Hi guys, Miss O'Connell here. So we're going to start out with example number 9 from the guided notes. This is an AP based example. So in example 9, we're given a block on an incline. We're given the lengths of each of the sides of that inclined plane. We're also given the weight of the object. We're also told that there is no friction, so that friction is negligible. So we do not need to consider or include friction in our free body diagram. We're asked to find the acceleration of the block and then the normal force as well. So our first step with these, as detailed in the last video, is to draw the free body diagram for our object. We're going to make the surface of the incline the x-axis. Right, the x and y axis are arbitrary, so we get to assign what's technically the x perspective and what's the y perspective. So we're going to rotate the angle of the incline so that the surface is along the x-axis. Force is acting on our box, or our block here. We have the normal force, or the force of the surface, which is going to be perpendicular to that surface. There is no frictional component. There is no force of friction, so we're not going to have friction in the x or the y. But technically, our force of gravity vector, when we rotate our axis, our force of gravity vector is going to flip down and to the right. We can either call that F sub g or w. They mean the same thing. Okay, so W is weight or force of gravity. Weight is the downward pull of Earth's gravity on an object. So weight is force of gravity. Up to you which equations you want to, which variable you want to use. We also know that the angle between the weight vector and the y-axis is the same as the angle of the incline. But conveniently enough, they did not give us that angle. Okay, so this is an AV problem. There's always a trick involved. We don't know the angle. We do know the side lengths of the triangle though, so we can find that angle using trig. So because we have all three side lengths, we could really use any trig function. But let's use tangent. So to find the angle between the force vector and the y-axis, we need to find the angle of the incline. So I'm going to take the inverse tangent of opposite over adjacent. So my opposite side is 3 meters and my adjacent side is 4 meters. So my inverse tangent, we get 36.86 degrees. My computer is freezing. There we go. Okay, so 36.86 degrees. Now that we have the angle, we can break our vectors into x and y components. It asks for the acceleration. Technically, the object's going to accelerate along the axis of the incline, which is what we assign to be the x-axis. So there's only going to be acceleration in the x direction, technically speaking. So we want the acceleration in the x. We're going to use Newton's second law in terms of the x components to find that acceleration. We know that the force of gravity will have two components, a y and an x component. The x component of force of gravity is going to be mass times gravity times the sine of theta. Because theta is measured with the y-axis, x is always cosine unless we're on an incline. So the x component of a vector is always cosine unless it's on an incline. Sine slides over and takes cosine's place. So when theta is measured with the y-axis, to find the x component of a vector, we use the sine of theta. And we're not technically given mass directly, but we are given the weight of the object. What's nice about this equation is that mass will actually cancel out. So we don't need to technically solve for the mass from the weight. If we divide both sides of the equation by m, it cancels out on both sides of the equation. So that saves us a step. So acceleration in the x direction is going to be g times the sine of theta. This is actually a shortcut equation that works every time if there's no friction. So if there's no friction on an incline, you can find the acceleration of that object down the incline by multiplying 9.8 times the sine of the angle between the incline and the horizontal. So that's it. On an AP exam, that's a great way to save some time. Again, but if this is if there's no friction, no force of friction, meaning mu is equal to 0. That's a nice shortcut equation that will work every time. Also on the AP exam, right, we use 10 instead of 9.8, so it'd be 10 times the sine of 36. So let's just evaluate that real quick. I hate writing 10 for g, but here we go. So let's assume that g is 10 meters per second squared. 10 times the sine of 36.86. And we'll get the acceleration in the x direction. Which will round to 6 meters per second. Okay, part B, normal force. So for normal force, the normal force is perpendicular to the incline. So that means that the normal force is going to be equal to the y component of the force of gravity. There is going to be no acceleration in the y direction. The object's not going to move through the surface of the incline. It's moving along the incline. So we're going to use Newton's second law, except the sum of the forces are equal to 0. Normal force is positive because it's pointing up. Force of gravity, the y component is going to be mass times gravity times cosine of theta. So we find, just like proven in the last video, that normal force is equal to the y component of the force of gravity. Okay, for this one, there is no shortcut. We do need to find the mass, which is technically 10 newtons. So you plug in for this, we're going to have normal force is equal to 10 newtons. Ran out of room a little bit here, so I consolidated, but we have normal force is equal to the weight of the object, 10 newtons, times the cosine of 36.6 degrees. And we find that the normal force is equal to 8 newtons. Okay, so another nice equation that will make some multiple choice problems on the AP exam a little bit easier if you have that memorized. Okay, example number 10. A 4 kilogram block slides down an incline at constant speed from the diagram above. Find the coefficient of friction for the block and the incline. So if we're asked to find the coefficient of friction, we're asked to find mu. That means that there has to be friction, that we're including friction in the problem. If it's moving at a constant speed, that means that it's moving. So we're talking about kinetic friction. We're looking for mu sub k. But constant speed tells us that there is no acceleration. The direction of the object isn't changing. It's moving down the incline, and the speed is the same. So that means that there is no acceleration. Okay, force is acting on our block. So you know that we have the normal force, which is perpendicular to the incline. For this problem, when we straighten out that incline and make the surface of the incline horizontal, the force vector is going to shift down and to the right at an angle of 30 degrees with the vertical. Let's call it weight. Why not? W. We know that there is friction. So friction is going to be on our diagram, and we know it is the force of kinetic friction, and that's going to oppose the motion of the object. So if the object is going to be accelerating down the incline, that means that the force of kinetic friction is going to be pointing in the opposite direction. I should probably draw that a little smaller. Hold on. Make that a little bit clearer. Okay, so force of friction is going to be in the opposite direction here. But if it's at a constant speed, that means that there is no acceleration in the x direction. So that means that the x component of the object's weight should be the same length as the force of kinetic friction vector. Because the net force is going to be 0. So we want that length to be represented as the same length there. Okay, so to find the coefficient of friction, we're going to have to sum the forces in the x and the y direction. Doesn't matter which one we do first, but we sum the forces in the x direction. In the x direction, we have the force of kinetic friction and the x component of the object's weight. So technically here I have force of kinetic friction is going to be negative, so I have negative force of friction. The x component of the object's weight is pointing in the positive direction, so I'm going to have positive mg times the sine of theta all equal to m times a. Again, we're looking for mu. So in order to find mu, we need to translate this equation to have mu in it. So force of kinetic friction is equal to the coefficient of kinetic friction, u sub k, times the normal force. So we need this equation in terms of mu in order to solve for mu. So we're going to substitute in for the definition of friction. The definition of friction is the coefficient of friction times the normal force. Again, that whole quantity is going to be negative. Rest of the equation is going to stay the same. Okay, we can simplify this a little bit more if we can find an expression for the normal force, F of n, which is actually a force in the y direction. So if you remember from the last example, we sum the forces in the y direction. The object will not accelerate through the surface of the incline. So the sum of the forces in the y direction will be equal to 0. So that means that the normal force should be equal to the y component of the object's weight, which will be mass times gravity times the cosine of theta. So we can substitute in for that into our equation as well. And you'll notice some things will simplify here. So we have negative mu sub k times m times g times the sine. Excuse me, that should be cosine. Normal force is cosine of theta. Plus m times g times the sine of theta. All equals m times a. So it's nice here, they did give us mass, but we don't need to plug in for mass If we divide each term by m, it'll cancel out completely. So we're left with negative mu times g times the cosine of theta plus g times the sine of theta is all equal to acceleration. Okay, if you remember back to the beginning of the problem, acceleration in the x direction is a big fat 0, so this is going to be equal to 0. To solve for mu, we're going to add it to the other side of the equation. So we have g sine of theta is equal to mu times the cosine of theta times g. Last step, to simplify, we can divide both sides of the equation by g cosine theta. You'll notice that the g's will cancel out. Such a beautiful manipulation here. The g's will cancel out. So mu is equal to sine over cosine, which is technically the tangent of theta. So this manipulation just proves that mu is a constant value without units, because the tangent of an angle doesn't have units, it's a constant. Okay, this is also a good equation that if you can memorize, awesome. If not, you can do the manipulations. You could have also plugged in way in the beginning. That would have worked too. Okay, but very simple. We take the tangent of 30 degrees to find the coefficient of friction between the inclined surface and the surface of the block. And we get 0.58 is our coefficient of kinetic friction. Okay, number 11. Just kidding, I labeled that wrong. This should be 11, but it's example 10, number 2. So we have a sled sliding down a hill with a constant velocity. The sled and the hill have a coefficient of friction mu sub k. Find the angle theta in terms of weight and mu sub k. So we sort of already did this, but let's take a look here. So if you want to get specific, in our last question we found through that manipulation, right, velocity in the x is still constant. So all the information that we derived and explained in the last question still applies here. It's just a new object with a new weight. And we're asked to find an expression. So basically we know from our variable manipulations in our last question that mu sub k is the tangent of the angle between the incline and the horizontal. So if you want to solve for the angle, right, to get theta by itself, we would take the inverse tangent of mu sub k. So if you know the coefficient of friction and you don't know the angle of the incline, you can take the inverse tangent of mu sub k to get that angle. And just to prove that to you from the last question, so we found mu sub k to be 0.57, which I believe we rounded to 0.6, but we'll keep it at 2 decimal places. 0.558, actually, 0.58. So when you plug that into your calculator, you do get exactly 30 degrees, which was the angle of the incline for the last problem. Okay, so that does work. So an expression in terms of weight, the weight actually cancels out, mass and gravity can't cancel out. So for an expression, we take the inverse tangent of mu sub k. Okay, next up, tension problems. Okay, so example number 11, which is technically the 12th example here. A person with a mass of 50 kilograms suspends herself from the lower end of a hanging rope. The upper end is attached to the ceiling. what is the force and the direction of the rope on her? So what force and direction does the rope exert on her? And then what is the tension at the top of the rope? All right, so let's give this a shot. So here we are looking for what forces are acting on her at first. You can see the diagram here. So if we draw the free body diagram for the person, I'm just going to use this dot to represent her center of mass, FBD of person. We have the downward pull of gravity or weight, which is going to be straight down. And then the opposing force we have is the force of tension, which is any force from a rope on an object. Suspend means that there's no acceleration, either the x or the y. It's not accelerating, it's stationary. Newton's first law tells us that objects that stay at rest want to remain at rest. There is no acceleration. So we can find the force and the direction that the rope exerts on her by using Newton's second law and the y, and setting the force is equal to 0. So the tension is going to be in the positive direction because it points up. Weight is going to be pointing down, so it's going to be in the negative direction. So we have tension minus weight is equal to 0. We figure out that the tension is equal to the weight of the object, which is mass times gravity. So tension is going to be positive in the positive direction, or 90 degrees to the vertical. If we use 10 for G, this does make it easier. So we have 50 times 9.8, or 50 times 10 on the AP exam. We get 500 newtons. Is the force of the rope on the girl. Force of the rope on the girl is 500 newtons, and that's in the positive direction or up. Part B, what is the tension at the top of the rope? Tension at the top of the rope is still going to be 500 newtons. But the force on the actual rope is going to be in the opposite direction there. It's going to be pulling down. So it's going to be negative 500 newtons for the force of the rope, the person on the rope. The force of the rope on the person is 500 up. Okay, example number 12. A series of masses are connected by a cord and are accelerated at 4 meters per second upwards. A, B, and C are tensions in the connecting cords. What is the tension in the smallest cord? So what is the tension of the smallest tension? Okay, so if you think about this as you're falling off of a cliff, right? And you have 4 people connected by a rope. These are the 4 people here. Which person would you rather be? Well, you'd rather be person A, because you technically have less tension acting on you, right? If you're the 10 kilogram object, you have the weight of all of the masses in series below you. A common mistake that people make is we think that if 5 kilograms is the least amount of mass, then the smallest tension is going to be C. But that's technically not true. C, the tension in C is accounting for the tension in B and A as well. So A is actually the best spot to be in. A is going to experience the least amount of tension because it has the least amount of weight opposing it. So our free body diagram here, we're going to have the force of gravity due to just the 20 kilogram object. That's going to be equal to the objects, or technically not in this case actually. Acceleration, if acceleration was 0, they'd be equal to each other. but we're told in this problem that the system is actually accelerating upward. So acceleration is 4 meters per second per second. So that means that our acceleration vector, our tension vector rather, should be larger than the force of gravity vector. For the object to accelerate upward, the net force has to be up in that direction of acceleration. So here we're going to sum the forces in the y direction, set them equal to mass times acceleration in the y to find the tension. So we're going to have tension minus the force of gravity, which is mass of the object times gravity. That's going to be equal to mass times the acceleration in the y. We know that to get the tension by itself, we'll add m times g to both sides of the equation. And we can plug in. So mass of the object is 20 kilograms. Acceleration in the y, we're told, is 4 meters per second plus 20 times 10 meters per second. So we simplify here. We get 80 plus 200. We get 280 newtons is the smallest tension force. Okay. Next one, number 13. A box of weight W hangs on a O-ring and 2 other cords. One attached to the ceiling, the other one attached to the wall. Find the expressions for the tension in each of the 3 cords in terms of the weight W. So on the AP exam, they'll tell you in terms of which variables they want you to solve the equation for or the expression for if they do not give you numbers. So this one is not going to be in terms of numbers. It's going to be in terms of variables, and they want one of the variables to be W. Okay, so if it's suspending or hanging from the wall, the acceleration in both the x and the y directions are a big fat 0. We're given the angle between the fixed support and our rope here. What we're actually interested in for our free body diagram is the angle between our rope and the horizontal. If you remember back to geometry, these 2 angles here make that Z formation. So you have alternate interior angles. So if this angle is 60, this angle is 60 degrees. Okay, and T2 is completely horizontal. It's at a 180 degree angle. Cosine of 180 degrees, you'll get -1, which just tells us that this force over here is negative. So for this one, I'm going to show all the work and make a T-chart. So we're going to list the force, the x component of that force, the y component of that force. Okay, so force is acting here. This is interesting because technically, if we're looking at just the weight here, tension 1 is equal to the weight of the object. So we actually don't need to consider tension 1 because tension 1 is the weight of the object. So tension 1 is going to apply that weight to this O-ring in the center. So if we draw a free body diagram for the O-ring, T1 is going to be equal to the object's weight. So that's the first force I'm going to put on here. Weight in the x direction is going to be a big fat 0, and the y direction is going to be -W. It wants us to leave the variables in terms of W. So we're going to leave W in there. No need to substitute in for m times j. Our next force, T3, our tension, one of our tensions. The x component is going to be positive because that tension force is up and to the right. So the x component is going to be positive. the y component is going to be positive. That x component is going to be the magnitude of the tension, T3, times the cosine of theta. The y component, because theta is measured with the x-axis, x is sine and x is cosine and y is sine. So x is always cosine unless it's on an incline. We're not on an incline. Theta is measured with the x-axis, so the x component is cosine of theta times the magnitude. Okay, T2. Two ways to approach this here. Again, technically cosine of 180 degrees, which is the position of T2. If you take cosine of 180 in your calculator and plug it in, you're going to get -1. When you take the sine of 180, you're going to get 0. So that tells us that there is no y component to the vector at all. There's only an x component. That force is completely horizontal, it's just in the negative direction. So the x component of T2 is all of T2. The entire magnitude of that vector is in the x direction. It is negative. There is no y component. Okay, so we want expressions for the tension in each of the 3 chords in terms of W. Well, we have one expression already. T1 is directly equal to W. To find an expression for T2, a little bit more complicated, but not too bad, we're going to have to sum the forces in the x and the y direction. Because this object is in equilibrium, meaning all the forces are balanced, it's not moving anywhere, the sum of the forces are equal to 0. So we're going to have T3 cosine theta minus T2 all equal to 0. So when we solve for T2, we get an expression that's not in terms of W. But that's okay, we can come back to it. So T2 is going to be equal to the x component of T3. If we find an expression for T3 in terms of W, we can then substitute in. Okay, so we have some expression for T2 right now. We need an expression for T3 in terms of W. So our next step is to sum the forces again, but in the y direction. Okay, I'm going to do that over here to the left. So we sum the forces in the y, also equal to 0 because the object is not accelerating. We have T3 sine theta minus W all equal to 0. So when we solve for when we solve for T3, we find that T3 is going to be equal to, we add a W to the other side, we divide it by the sine of theta to get T3 by itself. T3 is going to be W over the sine of theta. Theta is a constant. Okay, so we have the expression in terms of W and a constant. So that one works there. T3 is equal to W over the sine of theta. We could go one step further here and plug in for sine theta, because we know that theta is 60 degrees. So if we do that, we'll get W, the weight, over 0.8666025, which T3 ends up being 1 over 0.866. We get 1.15 times W. So some constant times W. Okay, so now that we have an expression for T3, we can go back over here and find an expression for T2 just in terms of W. So T3 is going to be 1.15 W, W as in weight, and then we're going to multiply that by the cosine of 60 and simplify. Okay, our final answer here, we have T2 is equal to 0.58 or 0.575 W. So T1 is equal to the weight of the object, T2 is about half of the object's weight, and T3 is 1.15 times the object's weight. So we have expressions for T1, 2, and 3 in terms of just W. Okay, this next one is a concept question based on the previous example. So a box is suspended in equilibrium as shown, which of the following statements is true? The tension in the horizontal cord is greater than the slanted cord. The tension in the slanted cord, meaning this cord over here, is greater than the horizontal cord, which is this cord over here. The tension is the same in both cords. The tension in the horizontal cord equals the weight. The tension in the slanted cord equals the weight. So take a minute, pause the video, and try this one on your own. Okay, so if we connect this to the last example question we looked at, the vertical cord, T1, is equal to the weight. The horizontal cord can only be equal to the x component of T3. So T2 is going to be smaller than T3. It's about 0.6 times the object's weight. T3 is going to be 1.15 times the object's weight. So in A it asks, or in part A it says that T2 is larger than T3, and that is not true. 0.6 W is not greater than 0.15 or 1.15, so that eliminates A. Our answer here should be B. T3 is the largest tension. It is greater than T2. T3 is not equal to T2. T2 is not equal to the weight, and T3 is not equal to the weight. So answer choice there is B. Same thing for this one, so pause the video, try example 15, unpause the video when you're ready to check your answer. Okay, for this one here, we should have gotten C. It's about 1/3 the slanted cord. Horizontal cord is about 1/3 of the slanted cord. So answer choice is C.